Hey guys, welcome back to chapter 4. In this video, we're going to look at, dive deeper into this idea of sharing electrons. So up until this point, we said covalent compounds, non-metal, will share electrons to fill everybody's octet. But just like life, that word sharing is not as straightforward as we would like it to be. So let's take a look at a picture and then we'll start to explain what's going on. So in this picture, I've got two different pictures. Both of these are hydrofluoric acid, HF here. We know this is a covalent bond because it's a nonmetal bound to a nonmetal. We see these two electrons being transferred. In the first picture, we've got the yellow dots are our fluorine, the white dots are our hydrogen. And in the first picture, those molecules are just kind of floating around at random. Some are facing up, some are facing down, some are facing to the left, some are facing to the right. But they're all just kind of like hanging out, mingling in any direction. In this second picture, we've turned on this electric field. So we've got a positive charge up here, negative charge down here. And what we see is something very interesting. When we turn on the electric field, all of the fluorines are pointing up, all of the hydrogens are pointing down. So what this tells us is there must be some sort of charge within this molecule, making it so that the fluorines are attracted to the positive and facing up, and the hydrogens are attracted to the negative and facing down. What causes this phenomenon, this kind of separation of charge, is something called electronegativity. So electronegativity is an atom's ability to attract electrons to itself. So while hydrogen and fluorine are sharing those two electrons, yes, they're not necessarily sharing them equally. It turns out that fluorine is actually kind of hogging those electrons. Okay? So let's dive into what is electronegativity? How do I know that fluorine's hogging? Here's what we call an electronegativity chart. This is something that will be given to you on your exam, not something you need to memorize. But this is a chart. It's kind of an arbitrary number assigned by Linus Pauling. And what he did is he assigned the atom with the highest electronegativity to be 4, roughly 4. And then everything kind of decreased from there. We've got the lowest electronegativity over here at 0.7. So what electronegativity is its ability for an atom to attract electrons. Does it make sense that fluorine would have among the highest electronegativities? Yeah. How many valence electrons does fluorine have? He's got 7. He really, really wants another electron, right? He needs 8. So he's probably going to make himself pretty attractive to those electrons, hoping to steal one or find somebody to share one with. What about these guys over here on the left? What about like lithium and sodium? Does it make sense that their electronegativity would be pretty low? Yeah, right? So sodium has 1 valence electron. He's actually kind of okay with that valence electron going away. He really has no need to attract electrons or bring electrons into himself. So he's not going to really care if he's attractive to an electron or not. So he's going to have a low electronegativity. So what we're going to look at is within these covalent bonds, what is the electronegativity of each of these atoms? And is that electronegativity close? And so, yeah, maybe they're sharing the electrons evenly. Or is that electronegativity very different and somebody's actually hogging the electrons? So if somebody is hogging the electrons, we have what's called a dipole moment. So a dipole moment is a separation within a bond where one atom has a little bit of a charge, and the other atom has a little bit of a charge as well. Okay. So here we see a bond between oxygen and hydrogen. In this bond, they are sharing electrons, but oxygen, with its higher electronegativity, is actually hogging those electrons or pulling them closer to him. So we see the electron density around around oxygen is really, really big. Well, if oxygen is hogging those electrons, what also comes with the electron? Yeah, the negative charge, right? So if oxygen is hogging the electrons, spending more time with them, with those electrons is coming the negative charge. And we have right here what's called a partial negative. So he's not stealing the electron. Stealing would be like a one whole negative, right? But he's just hogging them, so he gets part of that negative charge. And over here, hydrogen has a lower electronegativity. He's left in the absence of that negative charge because oxygen's hogging it. So the absence of a negative charge would be that positive charge. So the analogy that I always put forward here with the sharing but not equally, I have two sons. I've got a 10-year-old and I've got an 8-year-old, okay? They're like, Mom, can we run upstairs and play Fortnite? Sure, go ahead. Make sure you guys take turns. Make sure you share the PlayStation. Great, thanks, Mom. But are they actually taking turns? Yeah, they'll take turns, right? They'll share the PlayStation. But are their turns going to be the same length? No. Big brother is going to spend a lot more time on that PlayStation than little brother, right? Same thing happens with atoms. Technically, we're sharing these electrons, but big brother tends to hog the electrons and spend some more time with them, and little brother is left in the absence of electrons. So in this case, oxygen would be big brother, hogging electrons, getting that partial negative. Hydrogen would be little brother in the absence, having that positive. So how do we know who's big brother and who's little brother? How do we know if they're sharing equally or if somebody is hogging them? Well, the way that we determine that is by subtracting the electronegativities, okay? So if I'm looking at this hydrogen-oxygen bond, I go back to the chart. I see that oxygen has an electronegativity of 3.44. So he's right here. And hydrogen has an electronegativity of 2.20. So I would look at the difference. I would subtract those two values. So subtracting these two values, I get a difference of 1.24. Okay. So is that a large electronegativity difference? Is there going to be a separation of charge? We have this chart to help us out. If we subtract the electronegativities and the difference is between 0 and 0.4, we would say, you know what, they're sharing equally. Their electronegativities are relatively the same. Nobody's going to attract or hog the electrons, so they're probably going to be sharing evenly. So we call that a pure or non-polar covalent bond. Now if we subtract the electronegativities and we get something between 0.4 and 2.0, that's when we say, you know what, they are not sharing equally. There is a big brother, there is a little brother, and somebody's hogging them. So here we would have that permanent dipole, or that permanent separation of charge, and we have what's called a polar covalent bond. Okay, big brother and little brother. Now, just for completeness sake, if the electronegativity difference is greater than 2.0, somebody is pulling or hogging them so much that he just goes ahead and steals them. So this would be not sharing. Big brother just takes the PlayStation or takes the electron, and little brother is left without. So this is just another way to identify an ionic bond if it's greater than 2.0. All right, so let's take a look at an example. I want you guys to look at these three pairs of atoms. I want you guys to look at their electronegativities and see what type of bond they would be: pure covalent, polar covalent, or ionic. So pause the video and see if you can figure it out. All right, so the first one, SR, has an electronegativity of 1.0. Fluorine has an electronegativity of 4.0. So I'm going to subtract these two numbers. And I put them this way on purpose. Yeah, if I subtract these, technically it's 3.0. But we are really more interested in the just the magnitude or the difference in that change. So let's take the absolute value. It's 3. The difference is 3. Okay. So what type of bond would this be if the difference is 3? Well, that falls up here into the ionic region. So the bond between these two would be an ionic bond. And we know that too because it's a metal and a non-metal, so just kind of confirming that. All right, nitrogen and chlorine. So nitrogen's electronegativity is 3.0. Chlorine's electronegativity is also 3.0. So we subtract those two and the difference is 0. So this would be an example of a pure or non-polar covalent bond. And then the last one, we've got oxygen has an electronegativity of 3.5. Nitrogen has an electronegativity of 3.0. Subtract those two, and we get a difference of 0.5. So this would fall in this middle region and would be a polar covalent bond. So for funsies, if we're looking at this nitrogen-oxygen bond, we can determine who's big brother, little brother, and where that charge lies. So in this case, oxygen has a higher electronegativity, which means he does a better job of attracting electrons to himself, which makes him big brother. So big brother hogs the electrons, and he's going to have that partial negative. Little brother is left in the absence of electrons with his lower electronegativity, and so he's going to have the partial positive. So please practice this. I know it's probably something new and a little bit different. Please make sure you can identify this dipole moment or this separation of charge, because we're going to apply that to a more complex idea in the next video. I hope you guys found this helpful.